Hello everybody, today in this video we are going to discuss chemical equilibrium. Well, the chapter equilibrium is divided into two parts, chemical equilibrium and ionic equilibrium. So here we are going to discuss chemical equilibrium. The concept of equilibrium, as we know that suppose there is a reaction happening in this manner, X and Y combining together to form Z. Okay, then equilibrium is a point at which rate of forward reaction equals rate of backward reaction. Okay, at equilibrium, rate of forward reaction equals rate of backward reaction. And suppose the rate constant for forward reaction is Kf. Therefore, Rf equals Kf into concentration of X into concentration of Y. And the rate of backward reaction is Rb equals Kr, that is reverse reaction, into amount of Z. Okay, so Kf is the rate constant for forward reaction, Kr is the rate constant for reverse reaction. At equilibrium, Rf equals Rb. Okay, so at equilibrium, since Rf equals Rb, therefore Kf into X into Y equals Kr into Z, where X, Y and Z denoted in this form are the concentration of these species, these individual species. Okay, so here if we rearrange it, we get Kf upon Kr equals concentration of Z divided by concentration of X into concentration of Y. That is the product of concentration of products upon product of concentration of reactants. We call it as equilibrium constant or KEQ. Okay. Therefore, equilibrium constant is a measure of the point or the extent of the reaction at which the amount of product and the amount of reactants are constant. That is, they are neither increasing nor decreasing. Okay, so now equilibrium constant, if we denote it in terms of concentration, that is, here we are denoting the term equilibrium constant in terms of concentration, then we call it as Kc. Okay, C means concentration. And if suppose X and Y, here in this reaction X and Y and Z, they are in gaseous form. Okay, so if these species are in gaseous form, and if we represent K equilibrium in terms of partial pressure, where Pz is the partial pressure of constituent Z, Px is the partial pressure of constituent X into Py. Py is the partial pressure of constituent Y. Okay, so if we denote it in terms of partial pressure, we can write K equilibrium as Kp. P denotes pressure. Okay, now since from ideal gas law, we know that pressure equals nRT upon volume. We can also write it as pressure equals CRT, where C is concentration. Okay, so if we write partial pressure in terms of CRT, that is concentration of that particular species, into R into T, then we get a relation between Kc and Kp as Kp equals Kc into RT upon to the power delta N, where delta N equals total number of moles in products minus total number of moles in reactants. Now remember, we consider only those products and reactants which are in their gaseous form. Therefore, we consider only gaseous products and gaseous reactants while considering their number of moles. Okay. So suppose at temperature T1 and at temperature T2, suppose at temperature T1, we have K equivalent as, K equilibrium as K1, and at temperature T2, K equilibrium equals K2. Okay. Then there is an expression log of K2 upon K1 equals delta H. Delta H is the heat of reaction upon 2.303 into R. R is the universal gas constant into 1 upon T1 minus 1 upon T2. Okay, so this is the expression which expresses equilibrium constant in terms of temperature. Okay, now before moving on to ionic equilibrium, let's discuss some of the questions. Now question 1, it says that the value of log 10K for the reaction is, it is asking us to calculate the value of log 10K for this particular reaction. Now for this we need to go a little bit into thermodynamics, and there is an expression which relates delta G, that is Gibbs free energy, with equilibrium constant, and the relation is delta G equals minus 2.303 into RT log 10K equilibrium. Okay, so this is the expression between delta G and equilibrium constant. Delta G equals minus 2.303 into RT into log 10K. Okay, so let's go on how this question can be solved. We know that from second law of thermodynamics, delta G equals delta H minus T delta S. Okay, so if we take it in its standard state, then it simply becomes delta G standard equals delta H standard minus T into delta S standard. Well, since we are given with the value of delta H here, we are given that the value of delta S, we are given temperature as 298 Kelvin here. Okay, so we can calculate the value of delta G, and then if we substitute that value here, we can get the value of log 10K. So let's see what this value comes. The value of delta H is minus 54.07 kilojoule per mole. So we will convert it into joule first. So delta G becomes minus 54.07 into 1000. That is, we have converted it into joule. Okay, minus T, temperature is 298 Kelvin, into, since delta S, the value of delta S of reaction is 10 joule per Kelvin per mole. Okay, so we'll substitute it as 10. The unit for this expression is joule. So if we calculate the value of delta G, we get the value as minus 57050 joule per. Okay, so if we substitute this minus 5 point something that we have got here, the value of delta G, if we substitute it in this expression, we get the value as minus 57050 equals minus 2.303 into 8.314 into 298 log 10K. Okay. Now, in the question, we are already given the value of 2.303 into 8.314 into 298 as 5705. So, we will substitute it here. Minus 57050 equals minus 5705 into log 10K. So, from here, we get the value of log 10K as 10. So, this is the answer that you are supposed to get. And this question appeared in IIT JEE 2007. Okay. Now let's discuss another problem. The problem says that in a vessel, two equilibrium are simultaneously established at the same temperature as follows. N2 plus 3H2 gives 2NH3. N2 plus 2H2 gives N2H4. Initially, the vessel contains N2 and H2 in the molar ratio 9:13. The equilibrium pressure is 7 P0, in which pressure due to ammonia is P0 and due to hydrogen is 2 P0. Find the values of equilibrium constant Kp's for both of the reaction. Okay, we are given with pressure. We are given with the value of pressure here. Now pressure due to ammonia is also given. That is partial pressure of ammonia, and pressure due to hydrogen is given. Okay. Now we are given with the reaction also. Now we need to calculate only Kp's for all of these reactions. So let's try how can we solve this question. So the initial now we are given that the initial pressure of N2 and H2 is 9P and 13P respectively. Now initial pressure of N2, initial pressure of N2 equals 9P, and initial pressure of H2 equals 13P. So since the ratio of pressures are 9:13, so we have considered it that the initial pressure of N2 is 9P and initial pressure of H2 is 13P, so that if we take the ratio, it comes out to be 9:13. Okay, so the reactions are N2 plus 3H2 gives 2NH3. Okay, and N2 plus 2H2 gives N2H4. Now let the degree of dissociation in which NH3 is formed is X. Okay, so let the degree of formation of NH3 is X. Therefore here it will be 2X, and let the degree of formation of N2H4 is Y. Okay, so here N2, the pressure of N2 will be, initial pressure was 9P. Due to X, the loss is X, and due to Y, the loss is Y. And similarly for H2, it is 13P minus 3X. Here H2 has been dissociated in terms of 3X because 3 moles are there. In this reaction, it is dissociated in terms of 2Y because 2 moles are there. So minus 2Y. Okay, so at equilibrium, the pressure due to NH3 is 2X, due to H2 is 13P minus 3X minus 2Y, due to N2 is 9P minus X minus Y. So here also the same composition will be there. 13P minus 3X minus 2Y. Okay, so the pressure due to NH3, now pressure due to NH3 equals 2X. Okay, now the pressure due to NH3 in question, it is given as P0, right? So therefore 2X, it is equal to P0. So from here we get the value of X as P0 upon 2. Okay, now pressure due to H2, it is given as 2P0, since the pressure due to H2 is 2P0. So here 2P0 equals 13P minus 3X minus 2Y equals 2P0. So from here 13P minus 2Y equals 7P0 upon 2. We have substituted the value of x here. So we have got the value of 13p minus 2y as 7p naught upon 2. Now total pressure at equilibrium is total pressure at equilibrium equals 9p minus x minus y, that is partial pressure due to N2, plus 13p minus 3x minus 2y partial pressure due to S2, plus 2x partial pressure due to ammonia, plus plus y partial pressure due to N2H4. Okay. Now the total pressure is 7p naught. It is given in the question. So we equate it to 7p naught. Now if we simplify it further, then we get 9p minus p naught upon 2, x is p naught upon 2, minus, now 13p minus 2y. Just write 13p minus 2y as 7p naught upon 2. 13p minus 2y. Here y to y will get cancelled. So we are left with 13p minus 2y. Right here as plus 7p naught upon 2. Okay. So minus 3x plus 2x will be simplified to minus x. So minus p naught upon 2. It is 7p naught. So if we simplify it, we get 9p equals 7p naught minus 5p naught upon 2. Or from here p equals p naught upon 2. So here we have got the value of pressure as P equals P naught upon 2, and hence therefore 13 P naught upon 2 minus 2y equals 7 P naught upon 2, or from here we get the value of y as 3 P naught upon 2. Now we know the value of x, we know the value of y, we know the value of P, so we can calculate Kp's for both of the reactions. Therefore, for first reaction, Kp1 equals 2x squared. Okay, so just before that, to make you understand, Kp1 equals pressure due to NH3 whole square upon pressure due to H2 cube into pressure due to N2. Pressure due to NH3 is 2x, so 2x squared divided by 9p minus x minus y, that is pressure due to N2, into 13p minus 3x minus 2y cubed, that is pressure due to H2. Okay, so let's see what it comes into p naught upon 2 squared divided by 9 by 2 p naught minus p naught upon 2 minus 3 p naught upon 2 into 2 p naught cubed. Okay, so from here Kp1 equals p naught squared upon 5 p naught upon 2 into 8 p naught cubed. So from here we get the value of p naught as, value of Kp1 as 1 upon 20 into p naught squared. Okay, so this is our first answer, equals Kp1. Right. Now going for P2, going for the second reaction, Kp2, for second reaction, Kp2, it equals pressure, partial pressure due to N2H4 divided by partial pressure due to N2 into partial pressure due to H2 squared. Okay, so its value is y upon 9p minus x minus y into 13p minus 3x minus 2y squared. So from here, Kp2 comes out to be 3p0 upon 2 divided by 5p0 upon 2 into 2p0 squared. Or after simplifying, the value of Kp2 is 3 upon 20p0 squared. So this is what we were supposed to get. And now Kp2 is 3 upon 20p0 square and Kp1 is 1 upon 20p0 square. So from here we can say that Kp2 equals 3 into Kp1. This is the relation between both of these reactions. Okay, so let's discuss another question. The question says, in the following equilibrium, N2O4 gives 2NO2. When 5 moles of each are taken, the temperature is kept at 298 Kelvin. The total pressure was found to be 20 bar. Given that G naught F of N2O4 equals 100 kilojoule, G naught F of NO2 equals 50 kilojoule. Find delta G of reaction. The direction of the reaction in which equilibrium shifts. Okay, so let's discuss this problem. So the question that is given to us according to this, the reaction is N2O4 giving us 2NO2 grams. Okay, so in this case, reaction quotient or Q equals PNO2 squared upon P of N2O4, that is pressure due to NO2O4 squared upon pressure due to N2O4 equals 100 upon 10 equals 10 atm. Okay, so this is the reaction quotient for this reaction. Therefore, delta G of reaction equals, now since we know about that delta G of reaction equals delta G of reactions of product multiplied by their stoichiometric coefficient minus delta G of reactants. So delta G naught F of NO2 minus delta G naught F of N2O4. So from here we get the value, since delta GF of NO2 is 50 kilojoule and it is 100 kilojoules, so we get 100 minus 100 equals 0. So we can say that the reaction is at equilibrium, and hence since delta G naught equals 0, therefore Q equals K. Reaction quotient equals equilibrium constant. Okay. Now delta G equals delta G naught plus RT ln K. We know that, and since delta G naught equals 0, from here delta G equals RT ln K. Right. So from here the value of delta G is delta G equals 2.303 into 8.31 into, let's take it in atm liter. So this 2.303 into 0.0821 into 298 Kelvin log of 10. Okay, so from here the value of delta G comes out to be almost equal to 56.03 liter atm. So value of delta G is this. Now since it is positive, this is positive, Since the value of delta G is positive, hence we can say that reaction will shift towards backward direction. Therefore, reaction will shift towards backward direction. Okay, so this is the solution for this particular problem. So let's discuss another question. And the question says that at 27 degrees Celsius and 1 atmosphere, N2O4 is 20% dissociated into NO2. Now find A, Kp for dissociation of N2O4, percentage dissociation at 27 degrees Celsius and total pressure of 0.1 atm. What is the extent of dissociation in a 69 gram sample of N2O4 confined to 2 liter vessel at 27 degrees Celsius? Okay, so first part is Kp for dissociation of N2O4. We need to find the value of Kp for this dissociation. So let's see how this can be solved. The reaction is N2O4 gives 2NO2. Okay. Now let the initial pressure is 1 for N2O4 and 0 for NO2. Now at equilibrium it is 1 minus 0.2. Since 20% has been dissociated. Here 20% is dissociated. Therefore 20% means 0.2 of that particular initial concentration or initial pressure. Since initial pressure is 1 in magnitude, therefore it is simply 0.2. And here at equilibrium it is 2 into 0.2 equals 0.4. Fine. So therefore total number of moles at equilibrium equals 1 minus 0.2 plus 0.4 equals 1 plus 0.2 equals 1.2. So we have considered that initial concentration or the initial number of moles for N2O4 is 1 and for NO2 it is 0. Remember that concentration and moles, since the volume is constant throughout, therefore they are directly proportional. So let's take it the initial number of moles. Initial number of moles of N2O4 is 1 and NO2 is 0. And at equilibrium it is 1 minus x is 0.2, so 1 minus 0.2, and for that of NO2 is 2 into x equals 0.4. So the total number of moles at equilibrium comes out to be 1.2. Now mole fraction of N2O4 is, mole fraction of N2O4 is 0.8 divided by 1.2, comes out to be 0.66, and that of mole fraction of NO2 equals 0.4 upon 1.2 equals 0.33. Okay, therefore Kp equals pressure due to NO2 upon pressure due to N2O4 whole square. It is 0.33 squared, because total pressure is 1 atm. It is given in the question, therefore we need not write 1 here. So 0.33 squared upon 0.66, it comes out to be 0.165. Hence the value of Kp is 0.165 atm. Okay, so this is the answer for the first part of the problem. Okay, so the second part, it is asking us to calculate percentage dissociation at 27 degrees Celsius and total pressure of 0.1 atm. So that now the total pressure has been reduced from 1 atm to 0.1 atm. Therefore, we are needed to calculate percentage dissociation since the change in parameter has been taken place. Therefore, percentage dissociation will also get altered because the equilibrium constant gets altered. Okay, so let's try to solve this problem. Let alpha be the degree of dissociation of N2O4 at total pressure of 0.1 atm. Okay, so let alpha be the degree of dissociation. Degree of dissociation. Okay, degree of dissociation of N2O4 at 0.1 atmospheres. Okay, now therefore pressure due to N2O4 equals 1 minus alpha upon 1 plus alpha into 0.1. Because if we consider the reaction is somewhat like this. N2O4 is giving us NO2, 2NO2. So let the initial is 0.1, final it is initially it is 0, finally it will be 0.1 minus alpha, minus 0.1 alpha, here it will be 2 alpha. Okay, into 0.1. So if we calculate the total number of moles and then rearrange it, we will get the value of pressure due to N2O4 as 1 minus alpha upon 1 plus alpha into 0.1. Okay, so now let's find out what will be another the pressure due to NO2. Okay, now the pressure due to NO2 is 2 alpha upon 1 plus alpha, that is the mole fraction due to NO2 into 0.1, that is total pressure, right? So therefore Kp equals pressure due to NO2 squared upon pressure due to N2O4. It comes out to be 2 alpha upon 1 plus alpha into 0.1 squared upon 1 minus alpha upon 1 plus alpha into 0.1. So from here it is 0.4 alpha squared upon 1 minus alpha squared. So now it comes out to be now since we know that from first part a Kp equals 0.165 atmospheres here, therefore the value of Kp will remain same because temperature is same, and hence Kp equals 0.165. Okay, so since 0.4 alpha square upon 1 minus alpha square equals 0.165, therefore 0.4 alpha square equals 0.165 into 1 minus alpha square. Okay, so from here we get 0.4 alpha square equals 0.165 minus 0.165 alpha square. So if we simplify it further, we get 0.565 alpha square as 0.165, or if we simplify it, we get the value of alpha as 0.54. And therefore percentage dissociation equals 54%. If you multiply it by 100, it will be 54%. So this is the answer. This is the answer of the second part of this problem. Now, what is the third part asking us? It is, what is the extent of dissociation in a 69 gram sample of N2O4 confined to 2 liter vessel at 27 degrees Celsius? Now, the mass is 69 gram given to us. We know that the molecular weight of N2O4 is 92. Okay, so therefore let moles of N2O4 is therefore 69 upon 92 equals 0.75. So this is the number of moles of N2O4 that is given to us. Now let alpha dash be the degree of dissociation. Be the degree of dissociation of N2O4 at 27 degrees Celsius. Okay. Now, therefore, N2O4 giving us 2NO2, both in gaseous form. Now, initial number of moles is 0.75. Here it is 0. And if the degree of dissociation is alpha, then at equilibrium it is 0.75 into 1 minus alpha into 2 into 0.75 alpha dash. Oh, sorry, here it is alpha dash. Into alpha dash or equals 1.5 alpha dash. Okay, so therefore total number of moles equals 0.75. If we add both of them together, we get it as 0.75 into 1 plus alpha dash. Okay, now pressure due to N2O4 is 1 minus alpha dash upon 1 plus alpha dash into total pressure, and pressure due to NO2 is 2 alpha dash upon 1 plus alpha dash into total pressure. This is nothing but mole fraction of NO2, and this is the total pressure. This is the mole fraction of N2O4, and this is the total pressure. Okay, now since total pressure equals nRT upon V, right, N is the total number of moles, R is universal gas constant, T is temperature, and V is the volume of the vessel. Now, since the total number of moles is 0.75 into 1 plus alpha dash into 0.0821, that is universal gas constant, into 300 divided by 20. So, total pressure comes out to be 0.9225 into 1 plus alpha dash atmospheres. Okay. So, now let's come to Kp. Kp equals pressure due to NO2 divided by pressure due to N2O4, and this is pressure due to NO2 is squared. So, it is 2 alpha dash upon 1 plus alpha dash into Pt, total pressure, squared, divided by 1 minus alpha dash upon 1 plus alpha dash into Pt, total pressure. So, if we simplify it, we get its value as 4 alpha dash square into total pressure upon 1 minus alpha dash squared. Okay. Now, the value of total pressure is 0.9225 into 1 plus alpha dash. So, if we substitute this value of total pressure there, we get the value of Kp equals 4 alpha dash squared into 0.9225 into 1 plus alpha dash upon 1 minus alpha dash squared. Now, since we know that the value of Kp from first part of the problem is the value of Kp is 0.165 atmospheres, right? And since the temperature is same here also, therefore the value of Kp will not get changed. So the value of Kp is same, 0.165. Okay, so this makes a quadratic equation in alpha dash square. So if we solve this quadratic equation, we get the value of alpha dash as 19%, or the first, let's not consider it in percentage. We get the value of alpha dash as 0.19 or alpha dash as minus 0.24. So alpha dash is either 0.19 or it is minus 0.24. Now since the value of dissociation constant cannot be negative, therefore this value is not possible, and hence this is our required answer. Therefore extent of dissociation is 0.19. Dissociation constant is 0.19, and hence percentage dissociation equals 19%. So this is the answer. This will be the percentage dissociation if 69 gram of sample of N2O4 is confined to 20 liter vessel at 27 degrees Celsius. So that's all with this video. We'll come to ionic equilibrium in our next video.